This used to be what geometry was entirely about. Texas has made it to where it's part of the class, but not as much as it used to be. So anyway, a proof means that we're going to use logic to prove something is true. A proposition is just a thing that could be true or false. Proposition is just far too long for mathematicians to write. We don't like writing words, sentences, long words, short words, all of that. So we just stick some letters in there, usually P, Q, and R. So basically P, Q, R, those are going to be our propositions. Those are going to be the things that could be true, could be false. We've got and statements. So and means that both things have to be true. And this little kind of looks like an A without the little crossbar. You can use that symbol, and sometimes this symbol is used. This is a symbol for intersection, but I've seen both used. So basically an and statement, if both things are true, the whole statement is true. And if one of them is not true, then the whole statement is not true. The other thing is or statements. So that means one thing or the other is true. And this one looks like a V or a U. I've seen both used. This U is a union sign. This V, I mean, they both mean the same thing. This usually shows up in set notation kind of stuff. Anyway, so with or, it means if one of them is true, the whole thing is true. And if both of them are false, then it's false. We also have not. In most of my math classes, this is what the not symbol looked like, but in the textbook I use at my high school, this is what they use. Either one. Basically, not just undoes the proposition, whatever that is. So if P is true, then that means not P is false. We also have if-then statements. So an if-then statement is really important in proofs and math and all that. It's also really important in computer programming. A lot of computer programming is built entirely on if-then and for-while statements and that sort of thing. So anyway, if P, then Q. Or you can use this little arrow, because again, even if and then is too much for a mathematician to actually write. Even though that's only 6 letters between them. If they can use a symbol, they would. So there you go. They made a symbol. The converse means we're doing if then, but we're doing it backwards. So instead of if P then Q, it's if Q then P. You just flip it backwards. Inverse means you're going to do not P, not Q. And contrapositive means not Q, not P. So it's like we took this and kind of mashed them together. I'm going to set this one aside because I usually don't even remember those things unless I have to. Alright, truth table. The truth table means we're going to list all of the possible outcomes and figure out when our statement is going to be true or false. So the way we're going to start our truth table, for the first one, you're just going to do trues for the first half, falses for the second half. For the second one, you alternate true, false, true, false. If we had a third one, we'd have to modify it a little bit more, but we don't have a third one so far. Alright, so P and Q means both of them have to be true for this to be true. So P and Q are true. So this is true. Now, P is true, but Q is false here. They're not both true, so it's false. And here, P is false, Q is true. They're not both true, so it's false. And this last one, they're both false. false. Now P or Q means just one of them has to be true. So this first row, there's 2 true, so we're good. The second row, there's 1 true, so we're good. Third row, there's 1 true, so we're good. The last row, none, so it's false. I'm going to take something simple like this and then muck it up. So now we've got if P is true, then Q is true. So if P is true and Q is true, basically if P is true, then Q has to be true. So in this case, it's true. Now if P is true and Q is not true, then that means this if-then statement is not working, because this was true and that isn't, so that's not working. That's false. Now it also turns out that whatever P is on if-then, if it's false, it doesn't actually matter what's going on over here. So it's true here and true there. Why, you might ask? Whoever invented this said so. So someone said so. That's why. Alright, now for this one, we've got it flipped. So this would be the converse. Q, if Q, then P. So they're both true, so it's true. This one, Q is false, so it doesn't actually matter what P is. This one, Q is true, but that one's false. So that's going to be false. And in this case, Q is false, so it doesn't matter what P is. It's true. Alright, so now we've got not P. So if P is true, not P is false. P is true, so it's false. That's false, so it's true. That's false, so it's true. Not Q, again, if it's true, that means it's false. If it's false, then it's true. If it's true, then it's false. If it's false, then it's true. Now I've got not P. If not P, then not Q. That's how you would read that. If not P, then not Q. So I'm going to ignore this part entirely because I just did not P and not Q. So not P is false. So that means it doesn't matter what happens on the other side. It's true. Not P is false. So it's true. Not P is true. Not Q is false. So that means it's false here. Not P is true and not Q is true. So that means it's true here. That seems a little confusing. Practice is how you get better at this. Also, our proposition could be a statement. So for P, the sky is blue. For Q, we have a cold summer in Texas. So for P or Q, I don't know if y'all know, but I'm in Texas and it's hot. Heat advisory, I think the heat index is around 110, something like that. It's not cold out there. I don't need a jacket. Alright, so P or Q, the sky is blue, so that's true, but it is not a cold summer in Texas. So P or Q, one of those is true, so this would be true. And P and Q, this is false, so this would be false. And if we wanted to write these, this would be the sky is blue, or, I think you get the idea. You just stick the or the and in there. That should be good enough to get started.